নানারকম হার্ট স্ট্রোক হয়েছে কি ব্রেন স্ট্রোক হয়েছে কি জানি তোমার কাছে
Hello,
Yes,
am I
sir.
audible? Audible?
Yes,
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 sir.
sir. Yes, sir.
I
Audible.
thought given some trouble. I mean, it
Yes,
was
sir.
signal. So I had to log in Zoom, and that's why.
Sir, audible.
Audible. Okay, please go ahead.
Pushpin,
Yes.
Sir
As
has
sir has joined, shall we
joined.
start?
Please.
Yes.
Yes, introduce, sir, and after that.
Yes, yes, yes. Sir, shall we start now?
Yeah,
Sir,
please
are
go
you
ahead.
ready from your end? Yeah, okay. Very
No.
good evening, sir.
Good evening.
We are indeed privileged to have with us today an expert whose knowledge and experience have made significant contributions across diverse domains. We look forward benefiting from his expert knowledge, particularly today on quantum key distribution technique for security and authentication during this first technical session. It is my honor to introduce Professor Dr. Jyotsna Kumar Mandal, who is the professor of University of Kalyani, West Bengal. Uh, Dr. Jyotsna Kumar Mandal received his MTech in computer science from University of Calcutta in 1987, also awarded PhD degree in engineering in computer science and engineering department from Jadavpur University in 2000. Sir was working as professor of computer science and engineering, University of Kalyani. He was the former vice chancellor, Raiganj University, West Bengal. He was the former dean, faculty of engineering, technology and management of Kalyani University for 2 consecutive terms during 2008 and 2012. He was the former director, IQAC, and chairman CIRM, Kalyani University. Professor Mondal served as Professor Computer Applications, Kalyani Government Engineering College for 2 years. He has 38 years of teaching and research experience in coding theory, data and network security and authentication, remote sensing, and GIS-based applications, data compression, error correction, visual cryptography, and steganography. Dr. Mondal has awarded 31 PhD degrees and 4 are pursuing. He has supervised 3 MPhil, more than 80 MTech, and more than 130 MCA dissertations. Sir has published more than 450 research articles. Recently, he has published a textbook on reversible steganography and authentication via transform encoding from renowned Springer. This book has been translated into Chinese language and republished from China by the Springer. Sir has organized more than 70 international conferences and corresponding editors of edited volumes and conference publications of Springer, IEEE, and Elsevier, and Allieds. And he has edited 70 volumes as volume editor. Professor Mondal received Shiksha Ratna Award from Government of West Bengal, India, for outstanding teaching and research work in 2018. Highest 220 Scopus-based publication in last 10 years are already backed. Among all faculty members, 220 of the University of Kalyani. ISO World Convener of ISO IEC JTC, Teaching, Learning, Educational Technology. Professor Mondal is the governing council member of IETE India. He is also Eastern Journal Mentor of IETE Teaching at New Delhi. Without more further ado, may I now request Professor J.K. Mondal sir to deliver his lecture on quantum key distribution technique for security and authentication in our first technical session. Welcome you, sir. Over to you.
Thank you. I think I may have some problem in sharing my key, sharing my screen. So let's try. Otherwise, I have to go for some other laptop. I don't know. It's not allowing me.
Prashant sir, make JKM sir as a co-host.
Yeah,
He
let's
may
see.
not be
Please.
That
co-host.
is already co-host. That is
But I
already
have some
co-host.
problem in my laptop, maybe. I'm trying. It's just 1 minute. Just time.
পুষ্পেন
Yes, sir.
বলছি স্যারকে বলুন তাহলে পিপিটিটা সোমা ম্যাডামকে পাঠিয়ে দিতে বাপ তাহলে সেখান
না,
থেকে
আমি তাই করছি। I'm
হ্যাঁ
doing
স্যার
that.
না
হ্যাঁ
কিন্তু
স্যার
তাহলে তো ইয়ে করা অসুবিধা হবে স্যারের হ্যান্ডলিংটা আমি
হ্যাঁ, আমার পক্ষে একটু সুবিধা হতো। আমি ঠিক আছে, 1 মিনিট।
আপনি বলুন
আমি
স্যার, সেরকম হলে তাহলে
হ্যাঁ, আমি জাস্ট করে নিচ্ছি। ল্যাপটপটা কোথায় রেখে? ল্যাপটপ just 1 minute. I'm just sharing. Just wait, just 1 minute. It is already done. Actually, my Zoom credential is from ISO, so that given some security problem. Just I am just taking other laptop. Just updating the WhatsApp. So it has been configured for ISO because I am convener of ISO in Zoom. So this credential is given from the ISO. That is maybe a issues that they are not allowing others. But I have to resolve this, otherwise I cannot. Just 1 minute. Sorry for that. Asking for signing.
Sir, you may share your PPT. I can just.
Sharing, huh? Just 1 minute. Right. Zoom. You see, I'm joining in some other with other device, huh?
Okay.
Recording in progress.
Just I have to tweet other one. Just tweet.
Yes, sir. Your screen is visible now. Just unmute yourself,
Am
please.
I audible?
Yes, sir. Now you are audible.
Screen is visible, no?
Yes, sir.
Okay, fine. Actually, my Zoom credential is given by ISO. So that creates a problem in security. So now, sorry for that interruption for a few minutes. So now, okay, no?
Yes, sir. Yes, sir. You can continue, sir.
Okay. So now for the today's discussion, I'm again sorry for inconvenience caused for every one of us. So it is quantum key distribution technique for security and authentication. Actually, this is one of the burning topic nowadays. All of us knows about the quantum computing little bit. But here, my presentation will consist of something different. Why? The thing is that we are talking about the security. And in the era of AI, ML, and then quantum computing, all are burning issues. So we should start from the classical computing era or domain. to the neural computing, then your quantum computing. This three transition, I'll go for it. So mostly we are dealing with the communication sorts of things, and you see that when we are talking about the security is dealing with the exchange of information in secure manner. So if we need some exchange of information, so normally we can do it, no problem. So no complexity at all. But here you see that there are persons or third party who is taking my communication, because when I'm sending to receiver from as a sender, so there are flow of packets of transmission that I am sending, but eavesdropper is there to take my communication and to interrupt that and make change. That means there may be some bug in between if someone changes. That's why we there is a problem. That is a basic problem in all cases. Maybe classical, maybe your neural or deep learning, or maybe so in quantum computing. So in that case, what we normally do, we go for, in general, we go for the encryption in the source and then followed by the sending of encrypted key and received by the encrypted data to decrypt it. That means that may be a problem, not problem domain for the intruder. So this is the intruder problem. So now we think of that. Then is always this process is associated with some methodology. What is today's discussion? That means all of the cryptic system are depending on some key. Maybe your cryptography, maybe your steganography. So now if we think of very simple cryptography, I'm just giving you the background for a few minutes, otherwise it is very difficult to understand this. The thing is that we have two types of cryptic system normally, and there are various types of authentication methods and procedures. So in normal system, you see we have some symmetric key or we have some asymmetric. Now what is the difference between these two? I'm not going into any algorithm. The thing is that when I am talking about a symmetric key, that means only one key we are using. So if we are using a single key, that means the key is to be exchanged or key is to be transported, not exchanged. Transported through a secured medium. The key is to be transported through a secured medium. So I have to take that medium. If key is known, most of the cases algorithms are known and very good algorithms are there. Everyone knows this algorithm may be used. They can search the algorithm and use some computational machines and they can go for it. So key is a major concept and major concept for this. So for the symmetric, we go for a single key. But if you go to asymmetric, particularly you see the key exchange is coming from the asymmetric or public key. So either neural or classical or your quantum cryptography, key exchange technique is a major concern. Whether intrusion is there or not. Because you see, when I'm talking about the key exchange technique, in that case, what is happening? IoT transmission of your information, we are trying to compute something in terms of a mathematical computation and generating some private key and public key pair at both end of the transmission.
And this is vulnerable. So if we assume that the key exchange is vulnerable, then what can we do? How to make the key exchange secured is main purpose and main issue of this discussion. So, think of the public key, that is encrypt with the key and decrypt with other key. That means it is the second phase. That means the communication is always two phase. Please mind it, because this will be used later on, all these things. So that means a pair of key. How I know that this key pair you are using? How you know that this key pair I am using? That means an exchange has to be placed at the transmission and sharing of the key. That is most important concept and important paradigm of this system. All of these things are just and normally we use a diffie-Hellman key exchange technique. That means we used to generate some random numbers, we used to exchange some number, compute some modulus of some prime numbers and generate the key in terms of exchange. So this exchange, that means someone on the top of the wall can see the both of the side of the wall. Can see both of the side of the wall. That means that is the man in the middle. So this is the major problem in the diffie-Hellman key exchange technique. That if man in the middle is there, so it can intercept the key, it can change the key, and never knowingly by the sender or the receiver. Suppose you are giving me one brick, X, mark X, and I'm handing over the mark X bits to Y. So if I change the brick to Z to Y, so how Y will know that it is not X, it is Z? That is the problem of non-repudiation. That is not normally known in terms of the normal cryptic systems, and this key exchange is to be ensured that this is not suffer from the man in the middle attack. So you see that non-repudiation is cannot be ensured in encryption. It can be done by authentication. So authentication is another field of this cryptographic system where we used to go for a signature. What is the signature? The signature is computed from the text which you will transmit or the information you are going to transact with the receiver. It's a creator of messages creating with some algorithm. Normally we go for some hash function. So anyway, when I am talking about this cryptic system, you see that my problem domain is that you are exchanging the key through the public channel, and using this key, sender and receiver perform the complex mathematical operation. But if key is revealed by the intruder, now everything is revealed. And definitely we are taking a significant amount of resources while we are computing the key at both ends, exchanging the information and some mathematical computational result at both ends of the communication. So now, can we think? We have one receiver and one sender, and we are exchanging the key, and can it be one-way transmission of the key? Can it be non-transmission of the key, transmission of some other things? What I will address in my quantum system. Or can it be reduced the transmission or exchange of the key? Now, when I'm shifting from classical cryptography to state-of-the-art neural cryptography, we can reduce it. I'm just coming it a little bit. This research again started during 2003-4. That the researcher thought that is it always necessary that the exchange of the key prior to the transmission of the secret information is absolutely necessary? Yes. Key is there, exchange can be reduced. The number of exchange or exchange, can it be reduced? So that is another field come. Because the problem is that defilement key exchange. This is one example I have given here. That A and B are both agree on two large prime number 11 and 7. And then you see some random number is generated. Attacker is taking that number, you see. And the attacker is keeping that number and sending another number. You see here, it is very difficult for the receiver to see. You see, 3 and 9. You see here it is X, 8 and 6. It is getting not exactly whatever the number sent by the sender. That is called the man in the middle attack. And you see the computations are done and everyone is computing at the middle, at the source, at the receiver. This is one of the key exchange problem. How we can remove it? You see, if we go from classical cryptography to the neural cryptography now, how do we reduce? Here we use a neural network. And instead of exchanging the key, let's see a very, very primitive network, which is called the tree parity machine, where we take two neural network at two ends of the transmission. You see, identical structure of the network we are going for have the tree parity machines of A and tree parity machine of B. So we are initializing the random weight vector. Then we are executing the steps that you generate the random input vector. Xij belongs to -1 to +1. Then compute the values of the hidden neuron in terms of the signal functions. So Sgn x equal to -1, 0 and 1 if x less than 0, 0 or greater than 0, and using some weight vectors, the Wij, Xij here. Next, you see, after this computation, each end of the transmission will compute a number, either 0 and 1. If the numbers are not equal, we just leave it and go to the previous step. That means generate the weight vectors and random number. If it is equal, we are updating the weight vectors and edges both in randomly. And you see, believe that the both end of the transmissions we are using the different random number, not identical, but that things are also there. This is not my discussions of today. We can use some chaos theory and we can input some identical random numbers. And then at the end of some iterations, so all edges and all the nodes of both of the network will be identical. Now this is very difficult for the intruder to keep track of that and the exhaustive computation, because the intruder does not know about the exactly how many hidden layers, how many input layers, how many input neurons are there. That's why they have to go for the exhaustive computations, and at that time they can use. I think those who are interested, they can go for this book. This book is published by the Springer. All of these things are dealt with this book in 2020 during lockdown. I have written that book, and this book has also published, as the introducer told, that in Chinese language also by the Springer. So they are using that book also. So this is being used, so you can use that. And you see, we have used this in Java programming, and you see one window and one VMware we have used on the same machines, and we have tuned this network, and we have done all these things, you see, in a local loop only. So, and you see, these updation rules are there. We use that updation rule for updating the weight vectors. So that was some advantages of the neural synchronization. But you see, these are again classical sorts of things. Oh, and if we go to the quantum era, now let us again go for some primary computational aspects of the quantum computing. What are the primary aspects? The aspect is that, you see, we go for some. Normally, it is a quantum mechanics, that's a physics, and it is very powerful. And you see, it is very fast for computational aspect. But you see, in classical computing system, we use the bit or the voltage level of 0 and 1 or plus 5 volts or 0 volt or whatever, maybe less or others. I'm not going into that. So here it is not used in that way. Exactly, classical bits, that means 0 and 1, are not used. Rather, we use a qubit using the quantum phenomena of superposition to exist both 0 and 1 simultaneously. It's not independently. If you go for independent measure, that means the quantum state will convert it to a classical state, and no quantum system or quantum mathematics or quantum methodology will apply no more. That means, you see, that means you have two separate channel. One is your quantum channel, another was your classical channel. So when we are transmitting, computing, and doing everything, we are using a quantum channel. And when we are decoding it, we are using a classical channel. That means the entanglement is lost. So that state will not be available anymore. So this ability allow the quantum computer to perform many states. Normally we go for a state 0 and state 1 in classical computing system. But here I can go for, you see, 0, 0, 0, 1, 1, 0, 1, 1 if it is entangled. So 4 states we are getting instead of 1 state, and we are providing a significant speed advantage for computing the problem. So if we think of a single qubit, just I am going for the fundamental for your clarity and others, and then we shall go for the exchange technique. So here you see that here various bases are available. In a qubit computational basis, what are the bases? You see, this is a three-dimensional space. You can see my sphere here. It is not circle, it is a sphere. And we have an orthogonal system. What orthogonal? If you spread your thumb, your finger, another three fingers in 3 directions, the 90 degree to each other, it is an orthogonal space. Here you see, that means if you have a cube and you see in a one corner 3 sides of the cube, 3 lines are there. So that is the orthogonal space. And here we have, as it is a 3-dimensional space, so it is a 3-dimensional space, so X, Y, and Z. You see, suppose in a sphere, you may think of that this is an equator. So you see, you can shift to left to right, right to left, and you can go to the vertical in terms of the angle like this, and you can go for this direction. 3 directional aspects here, X, Y, and Z. So let us consider the orthogonal Z basis. What is orthogonal Z basis? The orthogonal Z basis is that, you see, is a Z axis. So this is a point center or axis 0, where X and Y and Z are coming up in 3 directional, both are perpendicular to each other. And this Z basis is called 0. And this lower Z basis is called 1. So we normally don't write this 0 and 1, we write like this 0, this bar, and this 1. So like this. This is a Z basis. So this is 0 and this is 1. Now let us go for the X basis. That means this is your X axis. What is the X basis? X basis of a qubit, 2 orthogonal X basis, 0 and 1, plus and minus, but 0 plus 1 divided by root 2. And 0 minus 1 divided by root 2. You see, plus IB. Here imaginary is not there. So you see this basis. One is called the plus basis. You see this is your minus basis, this side, and this side is your plus basis for x. And these are the formula for that. You see the basis. This is minus basis and this is plus basis. Let us consider the y basis. You see y basis means this side. This is minus I and this is plus I. So two orthogonal y basis state. We define these two orthogonal y basis state of a qubit. It's plus I and minus I. Plus I 0 plus I 1. Now here perfectly we are going for an imaginary concept. And we are considering an imaginary entanglement of the state. 0 plus I 1 by root 2 and 0 minus I 1 by root 2. So these two we are getting in the case. You see, plus I and this is minus I. That means is y. On a sphere, this is a 3D space. And we are thinking of when we are coming at, we are changing the phase. If we come from here to this side to here, if we come this side to here. So in all cases, we are changing a phase direction. That means the phase angle is a major contribution for this computational effect. These quantum computings are featured by 4 parameters or 4 concepts. One is called the superposition. Whatever I have already told that it is a decoherence, entanglement and teleportation. So used to say communication in terms of our classical system. But here we are thinking of teleportation in terms of key exchange and other things. So let us discuss these things. So what is superposition? It is one of the fundamental principle of the quantum mechanics. So a quantum state in superposition can be seen as a linear combination of other distinct quantum state. That means quantum state 0 and quantum state 1. So if we think of a qubit simultaneously exists in a linear combination of 0 and 1, not independently by 0 or by 1. So it is a linear combination of 0 and 1 where you see that a state psi equal to alpha of 0 plus beta of 1, where alpha square plus beta square equal to 1, where the alpha betas are the probability amplitude. Because your classical computing systems is a definite computation, but here we are thinking of a probabilistic terms and definiteness in terms of the probabilistic view. So I am thinking of a superposition where simultaneously 0 and 1 is exist and a state can be expressed in terms of the linear combination of 0 and 1. That is called the superposition. And let us consider decoherence. Decoherence means the loss of quantum behavior. Whatever we have defined in terms of the superposition of the multiple state as a single conjugate or a single composite state, the decoherence is the loss of quantum behavior, like superposition of entanglement due to unwanted interaction with the external environment. And until you are going for a quantum computing systems, so external environment cannot interact with that. It causes a quantum information to degrade over time and limiting the useful lifetime of the qubits and the quantum computations. So overcoming decoherence is a major challenge in quantum computing and tackled using techniques like quantum error detection and isolation of qubit from noise. That means it should not be degraded, it should not be interfaced with the outside classical state. And then what is entanglement? A pair of group of particles it entangle when the quantum states of each particle cannot be described independently of the quantum state of other particles. So it is a state of the particle, not like exact 0 and 1. It is a pair of group of particles, not a single 1 or single 0. So a pair of group of particles is entangled when the quantum state of each particle cannot be described independently. And the outcome of the measurement of one will always be correlated to other. That means when I am measuring 1, I can measure 0. And this is always the case when the particles are separated from each other by large distance. Not necessarily that it is a small distance. Or entanglement should be side by side or jointly embedded with one and other. So it may be with that. So now let us consider the teleportation. What is happening on the screen? Is someone doing thing or some attack is there? Hello?
He says something is moving.
So no, it's moving, but you see that it is some cross and other things are coming.
Yes,
Click and
yes,
cross.
yes.
So this I am not doing that. Who is doing that?
Procedure, sir, please ask the participant to not to do this and stop screen annotation from the participants.
Yeah, someone is annotating. Please, you see, I think please restrict them to do anything. Do not do that. You see, entanglement give the birth of quantum teleportation. So what I was talking about the quantum teleportation, you see, we have a classical channel, we have a quantum channel. You see? So we have the incoming photons and the transformation is done as the destination end. But entanglement is there, and when I am measuring the state, we use the Bell state measurement. I'm coming to that. In the Bell state measurement, we are going to do that. You see that. Let us consider. Now we are talking about the key exchange. So let us do that. You see, let Alice have A and D in the left hand side. Alice at A and D, and Bob has qubit B. Alice has qubit A and D. A, B are entangled. And the state of D is unknown, psi. Alice perform a Bell measurement A and D. Let's consider the measurements that are equal to classical bit. That means if it is a 2 classical bit, what are the possibilities? 2 classical bit, maybe 0, 0, 0, 1, 1, 0 and 1, 1. So Bob's qubit becomes a scrambled version. So Alice sent 2 classical bit, Bob applies Z, X, Z are both to correct. So Bob qubit now exactly psi. And Alice origin destroy, destroy, no cloning. You cannot clone it. Once it has been determined or once it has been decoded, so nothing is there. And you see, that is why when entanglement is there, this triangle you can think of that entanglement is there. But when you are talking about the decoding of the state, then that means this classical channel takes play of that. This classical channel takes play of that, and as a result, you see that original state will be destroyed and it will come here to a classical state. This is called the transportation. That means when I am talking about the key exchange in terms of the qubit and quantum key, so we have to go for this type of concept always. Now, what is there? You see that difference is that in quantum, we are not using 0 and 1, but in an entanglement. So, again, someone annotating. Is it someone doing on the, or I should just start again from the deleting the slide. Here you see, quantum you see irreversible logic. So, I think it has been converted. How it has been converted? You see that this side has been flipped. Your quantum computing, it is under research, is a probabilistic outcome, and massive parallelism we can go for it. Let's share once again. Someone doing some wrong things. It's very difficult.
Sir,
Huh.
once you will please switch on your camera, we will just take one snapshot.
Yeah, please. Please take.
Yes, sir.
Just 1 minute. I'm just. Okay. Just. Okay, may I go?
Sir, one minute, sir.
No, let us share again. There is
Yes, sir.
something problem. Yeah.
Yes, sir, your screen is visible.
Visible, no?
Yes.
Okay. But you see, the problem is that this has been exchanged because this right column will be the left column. Oh, okay. So you see, in a quantum computing, is a parallelism is massive. How it has changed, I don't know. Let us consider now the quantum gates, because in our concept, so concept will be discussed later on. So in our concept, what we are going to have, we are not only exchanging the basis, but also we are sometimes exchanging some quantum circuits for authentication. So some of the algorithm I shall discuss on that. So normally the quantum gates are reversible. All quantum gates are reversible, and if you go for U, is the conjugate transpose of U star. So I is the identity normally. And when I am talking about a qubit, it can exist either the basis 0 and 1. So is 0 is 1 0 and 1 is 0 1. So the quantum gates transform this basis state via unitary matrix, or I may say that gates. And you see, let us consider a single qubit gate. The first and simple gate is identity gate. It leaves the qubit state unchanged. If it is identity gate, that means it is a diagonal matrix. You see 1 1 0 0, it is I, and it is called the identity gate. Now we have another gate which is called the Pauli X gate. So equivalent to the classical NOT gate, flipping 0 and 1, where you see that in the right side X 0 0 1 1 is the flipping. It was identity 1 1 in the diagonal. There the diagonal is a 0 0. And let go for the Pauli Y gate. In Y gate, you see we have a phase shift. What is the phase shift? You see big shift, not only big shifts, but also it got a phase shift of the state. That's why you see 0 0, 1 become I, and you see this one become minus I. Means it is a shift of phase angle. So I have shown you the sphere, and I have shown that discussion there. Rigorously I have discussed there. And if you go for the Pauli Z gate, so it flips the phase of only one, not other. So here you see 1 is minus 1, not I as involved is here. And if you go to the Hadamard gate, it puts the qubit in an equal superposition. Then you see 0 is not here. 1 by root 1 minus 1, 1, 1. It is called a Hadamard gate. I shall use all of this, some of these gates for quantum key exchange. Then we have the phase S gate. It's applied pi by 2 phase on 1. That means again, you see, if you are changing the phase, that means some imaginary component as the pi by 2, and it is the positive direction pi by 2 towards the clockwise direction, it is coming as I. Now, we have discussed single qubit. Now we can similarly go for 2 qubit gate. How? You see C0, which is called the control knot, is flip the target qubit if the control qubit is 1. So what is control qubit? You see, like your Kano maths, this is 0, 0, 0, 1, 1, 1, then 1, 0. You see, this has flipped. This should come here, this should come here, and this should come here. But for the C0 gate, here you see this, because 1, 0 is 1, 1, and 1, 1 is the 1, 0. You see, these two rows, 2 columns are flipped. Because this column should come here, but it is actually here only. This is called the C0 or control knot gate. And here you see CZ, which is called the control Z. It's applied Z gate to the target qubit if the control is 1. And here you see that phase is changed here only. All are fine. Diagonal elements are 1. But at the end, when 1 is here, so its phase is changed here. This is called the CZ as control Z. Now, if we go for the C0, here each column of the matrix corresponds to the output vector. Here you see. So 0, 0 is okay, fine. 0, 1 is okay, fine. 1, 0 is 1, because 1 control is here. So it is being changed. You see here. It is come here. 0, 0, 1. And this one is come here. You see. This is called the control knot. And if you go to the next, control Z, each column of the matrix corresponds to the output vector of the input. So here 0, 0, 0, 1, these are not problem because control is not 1. Now next of the cases 1, 0, you see it's okay. And 1, 1, here we have both controls are 1. There is a phase flipped of the phase. That means 1 become to the -1. Then the phase has been flipped. And that is normally called the CZ, control Z. And let's go to the swap. The swap of the state of the qubit. You see, these 2 columns are swapped here. Here you see 0, 1 swapped to the 1, 0, 1, 0 swapped to the 0, 1. And if you go to the next here, you can see that finally swap gate correspond to the output vector of the input. So right hand side you can see the input. Yeah. You see 1, 0. So it should be here, but this 1 is here. And it should be here. This 1 is here. Now this one is fine. But you see the change is 0, 1. In 0, 1, you see this one, and 1, 0, you see this is 1. Means this is called the swap gate. Now come to the poly gate. CC0. It is called the CC0 gate. It's flip a target qubit if 2 control qubits are 1. If both bits are 1, then it will. You see both bits are 1. Then it will flip. Both bits are 1. So 0, you see 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. So like this, you see 8 is their combination for 3 bit. And that's why when 1, 1 you will get, here you see it is flipped. I am giving you some indication of this properties of this poly gate. Now let us poly gate. You see that in the 6th column 1, 1 is there. So it's changed. You see. Here. And also here. You see 7th column. Yeah. This one. These 2 are changed. Now We have heard about the Fredkin gate. It is called the control swap. Fredkin gate is called the control swap. Here, it swaps 2 qubit, condition that a third control qubit. Means, you see, green means here control bit, and blue means this is a target bit. So this, based on this, it has been changed. Then based on this computation, these two columns are swapped, and here it is written here clearly. So you can see that the Fredkin gate, each column of the matrix corresponds to the output vector of the input. And you see, in case of 1001, it is changing like this, and in case of 110, it is changing like this, and this has been reflected and shown in the previous slide. Now, I was talking about the Bell state. What is the Bell state? The Bell state is the specific quantum state of 2 qubit that represent the simplest and maximal example of quantum entanglement. And these are the representation of the Bell state. I plus like this 0011 0110 minus 0011 and 0110 1 by root 2 1 by root 2 1 is plus 1 is minus. You see, it's always 5 plus and 5 minus are conjugate type of things. Psi plus and psi minus also conjugate of this. Now let us think about a simple quantum circuits. The sequence of quantum gates acting on qubit, and a typical quantum psi bit, we have the qubit, where is the quantum wires initialized in 1, quantum gates, unitary transformations, and measurements operation. Project qubit into a classical bit. When I am measuring the bit, it will no longer in the quantum state. It will convert it to the classical state, and the previous state will not be exist again. It will be destroyed. So no cloning is possible. And classical control, you see, classical processing of measurement as a result is called the classical control of the same. You see, I can give a Bell state circuit here. You see, we have a Hadamard gate here. Circuit is 2, so gate count is here. It is a Bell state circuit. Now let us consider using all of this concept from quantum key distribution technique. So some of the techniques I am just discussing, and some results I will discuss. What is the foundation of quantum key distribution? So at the beginning we are talking about the classical key distribution. Then we were talked about the neural key distribution. Now we are talking about the quantum key distribution. What is that? It is create and share of a secret key through a quantum channel. Not the classical channel, neither the neural channel. And classical cryptographic algorithms are vulnerable to quantum computing. Quantum states cannot be cloned. That means there is no cloning theory yet for the quantum channel. And when an eavesdropper tries to measure, immediately the superposition is lost. So you try to measure the state, superposition will be lost. So there is no cloning. Cloning is not possible for that particular state. So we are talking about the quantum key distribution protocol. So this quantum key distribution protocol is divided into 2 classes. One is called the PM class and another one is called the EB class. PM class is called the prepare and measure, and EB class is called the entanglement based protocol systems. So let us discuss both of them. Let us consider first the prepare and measure class. Here, vendor creates a classical key and encode the classical key into quantum counterpart, which is called the prepare. That means first I am taking a classical key, then we encode the classical key into quantum counterpart using a prepare methodology. And corresponding quantum states are transmitted through quantum channel. That means the first step is to create a classical key. Second step is to encode the classical key into quantum counterpart, which is called the free pair. And the third step is corresponding the quantum state that transmitted through the quantum channel using entanglement or other. And what the receiver does, the receiver decodes, which is called the measure. That's why you see prepare and measure. You see prepare means the sender and measure means the receiver. The operation is performed at the sender is called the prepare state, and the operation performed at the receiver state is called the measure. That's why you skip PMQKD protocol. This protocol is named like PMQKD protocol. So the receiver decode the measure, sender and receiver do the classical post-processing. When post-processing is done, it is done using classical methodology. That means it is again an entanglement between the classical and quantum counterpart of the computing system. So these protocols are very well-known protocols. What are the protocols? BB84, B92 and SARG04 protocols. These are very well-known quantum key distribution protocol which use the PMQKD protocol. BB84, B92, SARG04 protocols are PMQKD protocol type. So I think you are able to conceptualize. Now let us consider the entanglement class of QKD protocol. That means EBQKD. This protocol is called the EBQKD protocol. Here, two qubits are entangled. How they are entangled? There we have the methodology I have already discussed in the prerequisite section of my lecture. So qubits are perfectly correlated no matter how far apart they are. They are correlated, but they are entangled. So there are some methodologies of entanglement. I have already given the mathematics of that. So one entangled qubit is sent to Alice and other is to Bob. So Bob and Alice at two ends of the communication systems, and by measuring their particles in specific base, they get correlated results that can form a shared secret key. That means first we are entangling the qubits, and based on the entanglement, one entangled qubit is sent to Alice and other entangled qubit is sent to Bob. And they are using their particle in specific basis. It may be X basis, it may be Y basis, it may be Z basis. I have already discussed that. And these are all correlated. And how far they are, it does not matter on this. So any attempt by Eve, that is man in the middle, to interrupt this measure, the particle disturbs and revealing her presence through statistical test, which is called the Bell inequality violation. That means if Eve is present, I'll show you in our results, some of the results. So any attempt by an Eve to intercept or measure the entangled particle, it disturbs the correlation. Because you see that bits, though it has entanglement, there is a strong correlation between two bits. So this entanglement and correlation give the main basis of intrusion detection. So if attempt to intercept the Bell inequality violation will detect that. It's a complete mathematical concept that you are trying to violate the correlation distribution, and your Bell's inequality violation will give you that there is a presence of Eve. That means intruder is there. That means we should reject that communication system. So what is the example of that protocol? It is E91 protocol. This is a famous E91 protocol of the system. So normally, if we go for M, so we shall compare with the BB84 protocol. Mostly whatever we have done some work. I will give you some glimpse of that. Oh. Now let us consider that QKT protocol with one-way basis. You see, we are thinking of two-way basis. When keys are exchanged, either in classical systems or neural computing systems, you see, the keys are exchanged through some computational methodology at the beginning. So we are talking about the key exchange problem. So if key is generated, so basis function is generated, now we can encode our data. Now, what is the philosophy of the what? You see, this is a PMQKT protocol. What I am talking now, some glimpse of the protocols I am giving you, the how it can be done. It introduces a decoy state mechanism. So we are thinking of a decoy state mechanism to enhance the intrusion detection. The protocol differs from the rest, is got the sender only basis. It's not the sender and receiver basis. So it reduces the overhead of a classical communication system. It's called the PMQKT, prepared and measure QKT protocols, and we are reducing the basis to unidirectional only sender. Receiver does not send any basis. But you see, in a classical system, in your public key cryptography, we used to exchange the data in both ways. That means receiver and sender, Alice and Bob. You see, they are exchanging the information. How? In terms of some computations of some, you see, then modulus operations with a prime number. But here really sender is sending the basis, not both sender and receiver. And result shows that the presence of eavesdropper, the bit mismatch increases up to 50%. So I can define or I can detect the intrusion detection in more effectively in this type of one-way basis. So here QKT utilize the quantum properties, superposition, entanglement, and no cloning. All three things are discussed here. Superposition, entanglement, and no cloning theorem. So in these PMQKT protocols, it have three phases. One is called the preparation phase, already I have discussed. Then it has the measurement phase, and third one is the post-processing phase. I have already discussed all these things. So let us consider that what is the layout of the work. You see, Alice is sender and Bob is the receiver. Let us consider that they agree on a key length n. So Alice transmit 2 n bits. And what are the basis? You see, this is one basis and this is another basis. Plus and cross. Let us see. And what are the polarization states we are using? We have to think of the polarization state also. Horizontal, vertical, diagonal, and anti-diagonal. All polarizations. H, V, D, and A, which is called the anti-diagonal. All polarization states we have used for the entanglement, and we have passes, encoding and measurement. For each cases, we have two passes. And only Alice announced the basis, not Bob and Alice both. And because you see, it is started with the classical communication overhead. And that's why in my picture, you will see that we have a communication classical channel as well as a quantum channel. We had a classical channel as well as a quantum channel. So here only Alice announces the basis and reducing the classical communication overhead, because one-sided communication is there, not both-sided communication. Let us consider the technique. You see, Alice randomly generate the classical, because Alice only sending, it creates the qubit, because only one unidirectional. If it is 1, then it is 1. If Alice randomly generate the basis A, B, I, then apply the Pauli X gate. Otherwise, you apply the Hadamard gate. And in phase 2, is created the qubit, and if beta equal to 1, then you have send 1, and then if Alice base equal to plus, then apply the Hadamard gate. Otherwise, you apply the Pauli gate. You see, now in 9, apply the Pauli X. You see, Alice, what Alice do? Alice bits, you are taking randomly generated bits and bases are used in class 2. This key concept of one-way basis enhancement. So, both sender and receiver are not using the basis and transmit the basis. Only one basis is received by the receiver and sender is taking. Now, what is done in the decoding phase? It is only Bob. And you see, Bob measures. Alice create, entangled and send. And Bob used to measure. So if BBI equal to plus, then Bob measure with the Pauli. Otherwise, it will measure with the Hadamard. Just opposite, you see. Here. You see, plus is Hadamard, otherwise Pauli. Here you see, it is plus is Pauli and then Hadamard. This is a decoding state. And it's getting the basis function. And then if it is base I, measure the Pauli, otherwise it's go for now come to the post processing. So you have got the basis and is publicly announces his basis, whatever be the values, and it get the Alice basis and Bob's key and a random fraction, this Alice key fraction, and one time pad we use, and then we used to decode it. Now let us consider two cases. So each sub-configuration following figure named as the tuple of the form P1, P2 and P3, a tuple. In absence of eavesdropper, P1 is the randomly generated classical bit by Alice. P2 is the randomly prepared basis by the Alice because it's the one-way hash. And P3 randomly prepared basis by Bob. So it is absence of eavesdropper. Let us consider that you are starting 0 and using a Hadamard gate. You see, it is just here. You see, Alice is here and Bob is here. You see, this 0, it's not net. You see, we have 4 different states with Alice and Bob. You see, here it is same state, here it is different. Here it is same, it is different. Here it is different, here also it is different. Now, if we go for the statistics, now let us consider eavesdropper is present there. What will happen in that case? So you see, we have a tuple of E1, E2, E3 and E4. Here you see one component of a tuple has been increased. Here it was only Alice and Bob. P1 and P2, it was done by the Alice, and P3 was constructed by the Bob. But here you see that E1 generated by Alice, E2 basis prepared by the Alice. Again, a basis has been prepared by the intruder, by Eve. And Bob should be there at 3 party. We have a man in the middle. And let us consider the configuration of that. You see, here we have the Eve and the man in the middle. And you see, 4 basis functions are there. And it is being transmitted. You see, we are getting various states in the presence of eavesdropper. And just I am going to, here it is very difficult to understand because all of the formulas I have given, these are being used and these are being done. Whether it is there or not, it is being, when it is being decoded, we are getting the values. Now let us consider the mismatch state. it is better to hear and understand the concept. The concept is that you see that this left side is the BB84 protocol. What is existing, and this is our without if post protocol. Whatever we have discussed, MQKT protocol. You see here, Alice encoding by H. Is bomb measured by H. You see, state was 0, state was 0. Fine, no problem. In our case, you see, Alice encoding with H and bomb measure with H. It was 0 and it is 0. No problem. In green states are on the same state, you see. But in this state, you see that 0 is encoded by H, but measure is done none. That means there is a difference in state. That means there is some suspicion. Here also you see nothing is there, but it has been taken H. So here you see X. Here we have a Hadamard gate. Here is a Pauli gate. Now you see these are the differences. You see, in case of absence of if there is no problem, absolutely our protocol is persistent with the BB84 protocol. Now let us consider the presence of if. Now consider the comparison with the BB84 protocol. You see, the green state has not any problem, and this states some same things, but definitely for the yellow state, you see that our protocol in presence of if, it can measure in a better way. How? Let us consider that. According to the algorithm described in the protocol, that we used to send the 400 times by generate 400 classical bits, because we are starting with the classical bit and following their quantum counterpart in two phases. That means 800 qubits are generated. The process is executed 1000 iterations in two states, and in presence of if and other in absence of if. And Alice has announced the 400 it. And let us consider the next step. Yeah. In absence of if, it is the same efficiency with the BB84 protocol. But in presence of if, the protocol has found 200-bit mismatch out of 400 bit. That is, the match percentage is more than BB84 protocol, while BB84 has got the 1/5 mismatch on an average. Mathematically, in terms of the positional mismatch, instrument detection capability is found around 50%. BB8 is calculated around 37%. We are getting two-fold benefit. What are the two-fold benefit? The two-fold benefit is that I am sending the basis from the sender only. But in BB8 protocol, so bases are sent in both ways. So one-way communication has been reduced, and in presence of if, it's giving much better mismatch of, that means the intrusion detection, you can go much better way through one-way basis detection, basis preparation and sending. You see, these are the same thing. We have that. This blue is your OW KT protocols. That where you see number of bits we are transmitting, and we are normally 1000 iterations we have taken for that. What are the features? Theoretical knowledge and the experimental results yields the fact that the number of quantum states increase with the number of quantum gates, and that are applied. An increased number of quantum states here is because of bits mismatch. in the one-time pad for the sender and receiver, because only sender sending the basis function. And from the verified fact from the experimental results, scope of the work, you can go for a better detection of the intrusion using the single site basis. That is, one site basis is reduced. Now let us consider another protocol. It's called quantum circuit transportation based QKD. You see, in the earlier case, what we were doing? We are thinking of sending the base or basis from receiver sender side only. So only some bases were transported and started with the classical computations, converted to the using the entanglement and sent. And we have detected in presence of if and in absence of if. In absence of if, we have got same identical results with the BB84 protocol. But in presence of if, we are getting much better. Where BB84 getting the 37% mismatch, where we are getting 50% with single site basis. But here, what we are doing? We are doing that we are trying to generate a circuit, and we used to transport the circuit. And it will entangle with the reverse type of circuit at the receiving end and try to compute the same, which is called the quantum circuit transportation based protocol. So the idea is very novel nowadays. They see, normally we transport the basis, not the circuit. So here it designed to distribute the quantum circuit elements over the quantum channel, not the classical channel. You see that the classical part is eliminated here. The classical part is eliminated here over the quantum. So we are sending this in the quantum channel. And after one successful circuit distribution between the communicating parties, same circuit can be used for any number of one-time pad of the specific length. So if one-time pad is different, the communication system will be different. What is the basic layout? It is we are using two single qubit gate, one Pauli gate and one Hadamard for circuit creation. And each line of the circuit, each qubit of the circuit may have the combination of 0, 0, 0, 1, 1, 0 and 1, 1. What are the meaning of that? 0, 0 means that the line has a Pauli gate, 0, 1 means a Hadamard gate, 1, 0 means a Hadamard followed by Pauli, and 1, 1 means the circuit Pauli followed by Hadamard. You see 4 combination of the circuits. So difficult for the intruder, which one is the circuit. So it is the one basis functions. Now you can change the basis after next. Or you can send only the padding systems. That means both way we can think of a situation. So that means we are sending the basis of constructing the circuit, not the exactly the circuit. So not computing as a primary classical computations and entangle with the quantum computation. And let's see here. So two primary bases we are used here. One is the rectilinear basis with two polarization state, horizontal and vertical, and other one is the diagonal basis with two polarization state, diagonal and anti-diagonal. Here we have used these various states, and this QCT QKD protocol tailing and leading padding is the same. That means we are using some padding bits at the beginning and the end, and this padding bits plays a very crucial role in detecting the intrusion. How we can go for it? You see, this is the estimation. Key length. We used to estimate the length of the key between Alice and Bob in absence of Eve in figure A and in presence of B. You see, here 50%, both A and B, and here Alice, Eve and Bob. You see, here 25% basis. And you see, we are defining the final key length of the mismatch, number of mismatch here. So we have used the 400 runs here, and you see that final key length, result of the shown in the previous surface the fact. Formation of one-time is n is the possible length through distribution of twice n, because we have two states 0 and 1, and we are going to entangle the bits. And how we are using the circuit? Here the methodology that 0 0 means the line of circuit as the Pauli. Already I have discussed bit 1 and bit 2. 0 1 means the Hadamard. 1 0 means Hadamard followed by Pauli. 1 1 means Pauli followed by Hadamard. That means we are giving the basis of forming the circuit, not the exact circuit. We are not transporting the circuit. It is not possible in that way. Already we have discussed. So total length of the classical bit stream in P plus C plus P. That means you see that quantum circuit of C by 2 qubits or C by 2 quantum lines, the intrusion testing each of length of the P bits. So what is the formula for that? QCN equal to 4 to the power n. Normally, you see, I am not going into 4 types of gates we are using for the possible lines. And now let us see the P circuit here. As an example, you see experiment 8 qubit circuit with 6 leading and 6 trailing pad means. This is leading pad and this is trailing pad and this is your circuit element. Where you see 1 1 0 0 0 0 1 0 1 0. So all circuit elements are here. So both of the gates are here. You see Pauli and Hadamard. Only Pauli, only Hadamard. Pauli followed by Hadamard. Hadamard followed by Pauli. So all gates are possible here. We have using, and we are using the same padding. Here you see the 2 Pauli. Here also 2 Pauli. Here only Hadamard in Q5 and Q19 and Q18. You see Pauli followed by Hadamard. Pauli followed by Hadamard. So this we shall detect the mismatch in terms of the padding also. And you see, I have told you that when the sender is sending the circuit concept to the receiver, receiver will go for a reverse computation. Then the circuit will be reversed. You see, in the previous cases, you see 1 1, it is X and H. Here you see reverse cases H and X. It is X and H in the sender and H and X in the receiver. This is we are going to have the opposite circuit. And leading padding and trailing padding bits are identical in both cases. In this case or previous case, either you are going for the reverse type of circuit or you are going for the identical type of circuit. But what the receiver construct the circuit, the sender construct the circuit, the receiver generate the reverse circuit. And you see, these are the analytical framework of the parameters of the total transmission bit, total padding bit, quantum bit error rate, error correction, estimation of the lower boundary, final key length, everything we have gone in terms of the computations here. These are given. I am not going to discuss. So you see smooth, minimum entropy and final key length, whatever we are using here. You see the length is this less than, these are the only the length. This is for the BBAT protocol. And this is for our protocol. You see, we have used a huge amount, and you see our protocol here only you see that. And let's see the efficiency for that. Here, these frameworks, you see, key rate per qubit. Here, you see, key rate per qubit is, you see, 0.31. But here, you see, key rate is 0.344. 6 is 0.289. This is your existing protocol system. If 199 is 0.1. So here quantum bit error rate. You see, these are the quantum bit error rates for that. What are the salient features for these protocols? Number of quantum states in the channel directly proportional to the gate density. So what you are going for the fabrication of the gate density as a basis functions, and it is depending for the type of gate. And when the circuit element is received by the Bob, he can immediately generate the reverse circuit at his own end. We are not using the identical circuit at both ends, and it is enlightened by the experimental fact that there is scope to extend the work by increasing the number of gates. You can increase the gate. So you have seen that we have made the comparison that we are getting better bit error rates than others. Now, another protocols we are thinking of, it's the decoy state DSQKD. It also follows the PMQKD, and it's called the rectilinear and diagonal basis only. And goal of the protocol is generate the one-time pad, and we are only decoy state we are using the Pauli X gate. How we are going for the encoding? Alice generate the n classical random bit. Again, we are starting with the classical random bit, the 0 and 1, and records this classical stream as a post-processing and convert this as a basis function using 0 and 1. What are the bases? Using rectilinear and diagonal. So we are using the rectilinear protocol and the diagonal protocol. And for each queuing, randomly generate the basis and apply the quantum gates, whatever gate you are using, and n encoded states are sent through single qubit quantum channel. You see, this is the same thing is given here, is create, and it is only here you see is ABI equal to plus, then it is using the Pauli X gate on quantum channel, and if it is not that, then it is using the Hadamard gate. Now, how decoding is done? Bob generates the random basis for qubits when it receives, and it applies the quantum gates based on the basis he has received already, and also apply the neutralize the effect of decoy operation of the Alice. So I have already discussed about the decoy operation, and now it's going to measure this state and alter the quantum state, whatever Bob measure, and it decided that how many states are changed by both cases. Then it decodes. That means from quantum to classical, it decodes. So when BPI equal to plus, it's measure the Pauli X, and otherwise it measure the Hadamard. So Alice and Bob publicly announces the generate basis through the classical channel. But for each matching basis, they have stored the corresponding classical bit to their respective key, Alice key and Bob key. And the further communicate the fraction of Alice and Bob key, find any mismatch. So it's a fraction of keys we are sending. And if they are got the mismatch, that is called the fraction. And then it will say, it will go for sending again. So this is the post-processing, whatever I have just tell you. Let us consider the results.
Excuse me, sir.
Yes.
Professor, they have joined. So
already, so I'm just finishing.
okay, sir. Okay, sir. No.
Within 2 minutes, I'm finished.
Okay.
I'm finished with the work.
No, sir, you continue, no problem.
No, it's okay. It's okay. Because I have some problem in my laptop. That's why I could not start it right.
Okay, sir. No problem.
So let us consider the result. In presence of Eve, you see protocol generated 62.5% mismatch in the transmitted bit. But in BB80 protocol, it has got 37 point. Again, you see all sorts of BB84 protocols, you see mismatch, it can generate not more than 37.5%. But here you see, we have extended more than 50%. In the earlier case, we have decided that it can define the 50% mismatch state. That means you see that again we are extending the mismatch state more in terms of the computation of decoy state and transporting the basis function accordingly. So you see, these are the result of this. Read your BB80 protocol, and it is SQKT protocol, whatever. The results I have got is a very, very good results we are getting and very good mismatch and better intrusion detection we are getting for that. So, the salient feature is that the experimental results is enhanced here. Number of bit mismatch computation is better, and number of intermediate quantum state within a quantum computation is directly proportional to the gate density of the communication. And it is experimental fact that the research work can be extended more. But the thing is that, this always we are using a classical channel and we are using a quantum channel. We are using an entanglement. We are using always here in our case, we are using the one basis function from sender side only. We are eliminating basis function from both sender and receiver. This is the main achievement of this type of work of quantum key exchange technique. But you can go for your entanglement things. You can use your basis function. You can use your circuit, what may be random circuits or whatever circuit. So this is my presentation in short. Whatever I do justice, I don't know. So what is the time? 8:10. So I have taken extra 10 minutes. So now I think over to organizer.
Yes, sir. Such an informative session it was. Thank you very much, sir, for your valuable deliberations. We already asked the participants to post their queries to the chat box.
Yeah.
But still we haven't received anyone. Our participants can directly
Yeah,
raise
they
their
can contact me.
queries.
Yeah.
Yes, or you may contact Professor Mandal. Once the FDP is over, we definitely will share the slides of these presentations once we can receive it from sir. Any more queries? Not yet received. So thank you again, sir. Thank you very much. Thank you very much, sir.
Okay, so I'll take some opportunity to, I think, calibrate my laptop from this ISO to here. So I'll do that. So let Debashis lectures be started. I'll be here. No problem. Okay.
Okay. Thank you, sir. Thank
Sir,
you.
Debashis, you can go ahead. Huh? Soma, you
sir,
can go ahead.
Sir, kindly share your PPT. We will share it with the participants.
I'll share. Don't worry.
Oh, okay, sir.
Thank you, sir. Welcome you all again to our second technical session. It is our honor to welcome an expert whose extensive knowledge and experience have made a lasting impact across multiple domains. Today, he will enlighten us with key insights on artificial intelligence and quantum edge, which will leave a lasting impression even after this faculty development program. Participants, you will be very happy to know that our theme of this FDP is suggested by this renowned academician. Please join me in extending a warm welcome to Professor Dr. Debashis Dey, a professor of Maulana Abul Kalam Azad University of Technology, West Bengal. Welcome you, sir. A brief introduction of Professor Debashis Dey. Dr. Debashis Dey is a professor in the Department of Computer Science and Engineering at the Maulana Abul Kalam Azad University of Technology, West Bengal, India. He is a senior member IEEE, fellow IET, and life member of CSI. He was awarded the prestigious Boycott Fellowship by the Department of Science and Technology, Government of India, to work at the Heriot-Watt University, Scotland, UK. He received the Endeavour Fellowship Award from 2008 to 2009 by DEST Australia to work at the University of Western Australia. Sir received the Young Scientist Award in 2005 at New Delhi and in 2011 in Istanbul, Turkey, from the International Union of Radio Science, Belgium. In 2016, he received the J.C. Bose Research Award from IIT New Delhi. In 2019, they received the Shiksha Ratna Award from the government of West Bengal. He published in 400 plus journals and 200 plus conference papers, 20 books, and was granted 4 patents. He has projects sponsored by AICTE, UGC, WPDST, DST, World Bank, AWS, and MEITY. He served as chairman of CSI and IIT Kolkata and AC member of IEEE ComSoc Kolkata. His H index is 48. His citation is 11,500. He is listed in top 2% scientists of the world and ranked 122 among the best scientists of India for 2025 by research.com USA. He is serving as associate editor of MST, Springer, IEEE Access, IJCS, Wiley, Elsevier, IIT Quantum Communication, especially EIC of IoT Frontiers in IoT, editor Hybrid Intelligence, Indoscience. His research interests are edge intelligence, IoT, and quantum computing. Now, we are eager to have the deliberations from Professor Debashis Dev. Over to you, sir.
Thank you to Pushpin Laidi for your kind introduction.
Thank you, sir.
Very glad to see around 100 participants have joined since 6 p.m. And this is a topic called quantum edge computing or quantum edge intelligence, where today for next 1 hour we'll be discussing on the basics of how this edge intelligence works and how this quantum computing actually helps this domain of edge intelligence. And we have heard already a very beautiful lecture from Professor Mandal that how this quantum key distribution happens. And this quantum computing is a old technology for almost 20-30 years is what it's there. But since you know that quantum computing works in the very low temperature, cryogenic temperature, so we cannot access the quantum computers directly, and that is the biggest limitation of quantum systems, that it is only at the it works only at the minus 270 degrees centigrade, where so that is the reason we cannot see these quantum computers in front of you. But thanks to cloud computing, we can access this quantum computer, maybe any part of the world, to the cloud. We can access as a service, right? Quantum as a service. So we call it quantum as a service, like a platform as a service, software as a service, infrastructure as a service. In cloud, we are using quantum as a service, right? And that is the reason we are getting these quantum computers. So people, those who are using this quantum computer, they cannot see it in front of them, but they can access the quantum computer either using IBM Q or by Google or by Amazon Bracket. So many software hardwares are available for direct access towards this quantum computer, right? So today we'll be discussing on basics of quantum. Already Professor Mandal has mentioned that how quantum things occurs and how it works. And today I'll touch the basics of edge computing and how it becomes intelligent, right? So it's a very interesting area of research that this quantum computing in India started in a big way. That you know that we do not have any hardwares. You know, in India we bring the hardwares from Taiwan, China, and many other countries. So we already lost the VLSI design, those design point of view, those VLSI chip design point of view. So I'm very glad to see that Government of India is working very hard for quantum mission. We have a NQM, National Quantum Mission. They are giving generous fund to the people, those who love quantum computing, quantum sensing, and other various areas of quantum computer. So this is a good opportunity for the quantum engineers to start the research and to contribute towards the society, towards various consumer electronics products. So let's see how it works. So you can see the term is called quantum age. We are in the age of quantum age, where quantum machine, quantum hardware, softwares, they used to accelerate with the superconducting quantum computing. As I've already mentioned that these quantum computers, they are in the superconducting mode, means cryogenic. So the material is superconductor and it provides quantum computing. And this quantum computing is going to the age of the devices. We call it quantum age, right? So before I start on the topic, we have the questions in mind. I think those who are listening to this talk, we have some basic questions in mind. Maybe some of you know it, but still we recap that what is age, right? What is the purpose of age and why we are calling it age, right? Then the question comes, what is quantum age? How this quantum is coming to the age of the device and providing services to the customers, consumers, right? And the third question, that is, what is quantum age intelligence, right? This is the topic of this all this 5-6 days FDP, quantum age intelligence, right? How to provide these machine learning techniques to the ages, how to provide various kinds of services to the ages, right? So first, see, in case of edge computing, you know that we have cloud servers. Cloud servers, only few thousands of cloud servers that we have. Then we have fog nodes. Cloud servers are maintained by, say, IBM, Amazon, and various other companies. Then we have fog nodes. Fog nodes are the hardware and software maintained by the enterprise. That means suppose your college, MCKVIE college, is organizing this event. So if they are using the Zoom server, I think we are in the Zoom server. Zoom is a cloud, right? Through this cloud, we are all 102 people. I can see they are all in this FDP, right? Next 1 hour we'll be discussing some of the topics which is related to the cloud. So your Zoom platform is nothing but cloud area, right? Where the data centers are there. And this fog computing is nothing but the intermediate devices in your college servers. We all work in various college, universities, and various other places, or even in the industry. The servers around you, they're all the fog servers. Cloud is much more powerful because they have petabyte, zettabyte of data, which can store huge amount of RAM it has. But if you come to our college level servers, it has around maybe 18 GB, 16 GB, or maybe maximum 64 GB RAM and some good hard disk. But if you come to the edge means the third layer, we have billions of devices. Your washing machine, your mobile phones, your laptop, your all the edge devices, even the taps, all the mobile devices, even your car is acting as a edge device, right? Now we have to bring this quantum computing in this level of edge, so that billions of devices can run faster. So what is the problem in the cloud? Because suppose we are in Calcutta and you want to access the Amazon server. Amazon server is in Mumbai. If you want to send the data from Calcutta to Mumbai, and it will come back. So a lot of several milliseconds of delays are there, right? So delay is the one problem. Communication cost is another problem. Data will go from Calcutta to various other places, router, switch, hub. Then they will come back to again to us. So it has a lot of cost is involved, delay is involved. So that is the reason we are using fog devices, and also we are using edge device, right? Edge device can perform huge amount of job because of nowadays we know that our mobile phone is also very powerful. We are calling it mobile cloud computing on mobile, where we can access the cloud servers and we can access all the data. See, in our mobile phone, it has 16 GB RAM, right? Many of us are using this huge RAM, hard disk, and everything. So these are the edge devices, which is actually making it possible, right, to work in this domain very faster. So if you think this edge layer, the billions of edge devices, that means all the consumer products. It can be washing machine, it can be AC, it can be refrigerators, it can be car, it can be your smartwatch. Everything is edge device. Edge means the device which is close to you. That is the reason that name is edge, right? Even some of the governments are also giving service. You know, earlier you have to go to say any government. West Bengal government also provides service at the edge. You know, in your club or in your locality, they come and provide service. Whether it can be Aadhaar card service or any kinds of PAN card, or it can be any municipality service, death certificate, birth certificate, or any mutation. They come to the edge of the user, and they can perform the job. So edge computing can perform this thing very fast, extremely fast, ultra fast, because they're closer to the human being, closer to the society, closer to the IoT device, right? IoT device is actually working hand to hand with the edge devices. So billions of IoT devices are there, and they can get the service from your cloud itself, means from your this laptop or mobile phone itself. They don't no need to go to the cloud, because if they can perform the job, the computation at the edge level, why they will go to the cloud? That will reduce the delay and it will increase the operation faster. So system will become real time, and that is the reason we are talking about edge computing or edge devices. Right? Edge computing is playing a major role for the development of the current technological scenario for IoT devices. Now, what are you calling it? Quantum edge. So we are providing these quantum computing services at the edge, right? To the server, to the quantum devices. This we are getting, the people are getting help. We are controlling the environmental parameters. We are controlling the CCTV. We are doing quantum communication. We just heard about the lecture on quantum key distribution, which is talking about quantum communication. It can be between two drones. It can be between two satellites or any other devices. We call it quantum communication, and we have quantum processor and other devices. So quantum edge simulators or quantum systems that can perform the operation, we call it quantum edge, right? Now, if you see the operations, means the warehouses, they are connecting to the edge devices, and these edge devices is directly connecting to the cars, IoT enabled cars, IoT enabled camera, IoT enabled traffic light, IoT enabled laptops, drones, and other various gaming devices. So these are the things layer. This is the edge layer. Top layer is a cloud layer or this fog layer, whatever. So this is the ecosystem, how the system works, right? So we want to provide this quantum based services. We want to perform the operations very fast in real time fashion. See the term real time analytics, real time response for the ultra fast communication, right? We heard about ultra fast bullet train and everything. It is only possible due to this 5G and 6G network, right? The backbone of this 5G and 6G network is based on quantum computing. I'm repeating, the backbone of this quantum computer means 5G and 6G is quantum computer, through which we are getting the services at the edge, right? It can be through Wi-Fi or through various other access. So this edge device can perform the real-time IoT applications with the help of quantum intelligence. Now, if you just go into deep dive, we are talking about nanotechnology, we are talking about quantum devices. Actually, quantum devices are the materials which is actually confined in a very small dimension. It can be below, say, 100 nanometer. So any material So suppose any gold, if you put the material in a less than 100 nanometer, it becomes, earlier it was bulk, means it can, energy is continuously varying. When you go to the quantum well, see the discrete steps. When you go to the quantum wire, the spike nature comes. In case of quantum dot, see all the dimensions are quantized. It is called 0D, means electrons cannot move. All the electrons are confined in a very small space. We call it zero dimensional quantization, right? In case of quantum well, quantum wire, quantum dot. Well, it can move in the well format, wire in the single 1D, and quantum dot is a 0D. And this is the basic principle of quantum computer, where the either device works in quantum well or quantum wire or quantum dot. So these are the three areas, right? So what you can see, the density of states, the number of electrons per unit volume, per unit space, space. See, energy is varying continuously. So this is for bulk, means without quantization. When we quantize more, so energy will become discrete. It will become more discrete in case of quantum wire, because 2D becomes 1D. Electrons can move in 2-dimensional in quantum well. But in case of quantum wire, it can move in only one direction. But in case of quantum dot, it cannot move. Electrons are confined. Electrons within a material is confined. So this is called quantum dot. See, quantum well, wire, dot, these are the basic principle of quantum computers. Actually, quantum computers are made up with this, either well, wire, and dot, right? So let's go move forward. And this is the quantum well formation, growth formation. These are the quantum dots, that which is formed using various lithographic technique or quantum dot formation technique, where materials are grown and it shows quantization effects at various wavelengths, say 1000 nanometer, 1060, 1300 nanometer. Various materials like indium arsenide, gallium arsenide. These are the materials which is confined like this. Now, why we are going for quantum computers, and what is the why we are using it? As you've seen the previous lecture, we heard about qubit. In classical bit, we are talking about 0 and 1, but in case of qubit, we are talking about 0, 1 and half, where 0 and 1 can also stay together. We call it quantum entanglement. They can have a same state at the same time. So if you see the quantum computation is logarithmic, 2 to the power n. In case of classical computer, you want to increase the bit. Okay. 7 to 8, how much it will increase? Pushpendu sir, are you there? How much it will increase? 7 bit to 8 bit. In case of classical, how much bit it will increase? Anyone can say?
1 bit.
Yes,
1 bit, right?
yes.
But in case of quantum computer, 7 to 8 means qubit, 7 to 8 means 2 to the power 7 to 2 to the power 8. Right? Huge jump of computational capabilities, right? 2 to the power 7 to 2 to the power 8 means how much? It is 128 to 256. So you can understand huge amount of computational speed will increase. And that is the reason we are using quantum computer. We are using quantum computer to make it faster, ultra fast computing, right? In case of classical, 7 bit to 9 bit, how much bit increase? Classical, madam. 7 bit to 9.
7 bit to 9 bit.
Yes,
So that means we are increasing 2 bit.
2 bit. But in case of quantum computer,
2 to the power 7, 2 to the power 9. So 2 to the
you
power
can
9 minus 2
understand.
to the power 7.
Huge. 2 to the power 7 means 256. Then after that 512. Then after that 1000 something will come, right?
1024.
Yeah, 1020. So huge amount of speed increase. in case of quantum computer. So in case of classical C, linearly increasing, right? One bit increase means one power. Power is increasing one bit linearly. But in case of quantum computer, it is exponentially increasing. Power is increasing exponentially, ultra fast, right? So ultra low latency devices, error rate and everything is very fast, and that is the reason we are using quantum computers, right? And this is the picture of a quantum computer. And I was fortunate. I don't know how many of you have seen it. I was fortunate to work in this kind of devices since 2004 to 2008 when I did postdoc in Edinburgh. Then also we use this quantum computers in MB techniques. We use this kind of primitive quantum dot structure we developed within this device, and it is ultra vacuum. This device goes within a vacuum, 10 to the minus 12 milliwatt, so low pressure and minus 273 degrees centigrade, ultra low temperature, Kelvin, 0 degree Kelvin. So you can understand so much low temperature and low pressure it works. Because you see, I've already shown you the quantum structure. Previous slide. This structure, quantum dots, does not exist, cannot exist in the room temperature. It simply vanishes, right? It only exists in the extremely low temperature, right? Low temperature, low pressure. So that is the reason we are doing this quantum states in this kind of vacuum chamber, right? I think many of you have seen this picture earlier. So it takes almost 15 days to make the vacuum. Okay, we used to use the pumps to make the vacuum and low temperature for liquid nitrogen and helium. So many other gases we have used for various temperature down, right? And we have to give continuously supply of liquid nitrogen because otherwise, there's a lot of heating inside, right? So these are the challenges that they're all in superconducting state. Right? See, this is the actual picture where this is the quantum substrate is there, very low temperature, high density superconducting wires. These are the control units, memory and so and so. And these are the temperature variation, right? How it varies. We cannot use it in normal temperature. That is the reason we connect the cloud at the room temperature to this quantum computer. So you heard about
What
IBM
does it
Q.
mean? 20 MK, 0.1 K, 4K, 77 K?
Yes. So these are the temperature variation. Means slowly gradually there are various chambers. Ultimately, this device goes to very low temperature. See? So only the various chambers are there. Multiple chamber is there. Right? The temperature is different in different place. Yeah. So interconnects can be stay in this temperature 77 degree Kelvin. This is almost 0 degree Kelvin, right? 0.1 Kelvin is almost 0. So very low temperature. Right? There is a gradient of temperature. Now we means the user, those who use IBM Q or Amazon bracket. We are taking the help of cloud, so that we are accessing the servers outside. See, these are the states, quantum states, which is this is the quantum bit. I already showed you this one, right? This quantum dots, right? These are the quantum dots, right? This is actually the real picture. Mind you, this is our own picture of quantum dot. We grown 2005-6 that time. So these are the qubit exist within every system, right? In classical we have 0 and 1. In qubit means you can see the arrow can be anywhere in the space. If you think of football kind of thing, this arrow can be any state. This is called block sphere, and the peak at the top is called 0, bottom is called 1. It has 2 to the 1 states. See, this is varying like this. It can have any state, 2 to the 1 number of states on the surface of the sphere. We call it block sphere. See, it is continuously varying on the surface, right? And if you change the angle, this picture is showing that various angles various phases, right? And this dots means that pointer changes its position, various levels, right? So these are all the quantum states. Now let's come to various quantum information system. Something is called quantum sensing, quantum networking, quantum simulations, and quantum computing. So these are the four pillars of quantum information system, right? So far we have discussed about how this quantum computer works. Now slowly we are going towards QIS, quantum information systems, right? Now see these states, as it is in very low temperature, there's a lot of noise is there within the system. There is a lot of noise, and that is the reason quantum computing is not yet mature. Mind it, it will take another 20 years. If you see the literature, the efficiency and all this quantum machine learning and so and so, it is not so uh, healthy, right? So that is the reason direct implementation of quantum computing is a problem, right? Because we are getting ultra sensitive environment. It is for a small change, quantum computer, the circuit noise comes, right? If the noise is high, it is not good for computation, right? Isn't it? If the noise level is high, if the error is high, then it is not good for quantum computing or quantum machine learning or this kind of any kinds of computation, isn't it? And that is the reason this quantum computing is a challenge till date. We are not the scientists, even the industry is not getting extremely good result for this kind of quantum computers. Now, as the problem is there, the sensitivity, it is good for these quantum computers are good for as a sensors. We call it quantum sensing, right? If it is bad for computing because the ultra sensitivity, so ultra sensitivity that means it is a very good sensor. Agree or disagree, Shobha madam?
Yes, sir.
So if it is very, it is ultra sensitive, so it affects the computing, right? But it is good for sensing, right? Because it is ultra sensitive.
Mm.
It can do very good sensing, right? That is the thing we are discussing. A lot of energy applications like energy systems, resilience, so many. So quantum sensing is a very interesting field. So edge computing, 5G, 6G, everywhere we are using these quantum computers, right? Quantum software. The Amazon also providing this quantum service using Amazon Bracket. We used to have a project on quantum bracket. So see, we want to provide this quantum repeaters, quantum switches, quantum computing units, in the end of the system. So in the edge processors, we are using this quantum sensing devices. See, edge servers, quantum processing unit, QPU, quantum repeaters, quantum switches. So these are the edge devices, endpoint, those who are using quantum applications. Right? Huge amount of application for the edge devices. So if you see the quantum computing, there's a quantum machine learning, quantum computing for calculation of various capabilities, quantum cryptography, quantum teleportation, quantum sensor, quantum imaging, quantum networking. These are already QKD is part of this quantum networking. So many applications are there using these photonic qubits. Now let's come to the sensors. When you're talking about the quantum sensing, if you compare the difference between classical sensors and quantum sensor, what is the difference? Classical, what is sensor? Anyone can say what is sensor? What is sensing? Sensor is a transducer which converts, right, non-electrical signal to electrical signal. Transducer, right? So if you see the measurement is in physical change, in case of quantum sensor, the change is in the quantum state, not in the physical state, right? So a lot of noise is involved in classical, but in case of quantum sensor, it is ultra high precision. Mind it, ultra high precision. So quantum sensors are so popular, is extremely sensitive. It is ultra high speed. This possible. So it is used for brain imaging, right? A lot of applications are there for quantum sensors. So quantum sensors used for quantum optics, laser system, atomic physics, cryogenics, and signal processing. So many applications for this quantum sensors. So the limitation of the classical sensing has been removed by quantum sensors. Quantum sensing is utilized by the principle of quantum mechanism to high sensitive states of the physical quantities, okay, suppressing the capabilities of classical sensors. So what classical sensor cannot do, quantum sensor can perform the job, right? So it can use the quantum entanglement, quantum superposition to perform this sensing applications, right? So there are three states.
But the cost will be more, no?
Quantum cost, quantum sensors. Yes,
Yes.
cost is high, but for good quality, you have to pay cost, right? Right. So there are three things: superposition, entanglement, coherence. These are the basic sensing principles, right? What is superposition? Quantum state can exist multiple states simultaneously. Quantum system can exist multiple states simultaneously to probe different measurements, right? Entanglement means one state is linked with other state, enabling the sensors to suppress the standard quantum limit, SQL. This is not that SQL we know. We call it standard quantum limit. So entanglement can remove that standard quantum limit because of entanglement property.
So what
Coherence
is
means
this
it maintains
SQL?
the phase relationship between accurate measurements.
So
Yes?
what is this SQL? Standard quantum limit? How much it is?
Okay, let me explain that. Everything there is a limit, right?
So
Yes or
there
no?
will be some standard limit of the quantum.
Yes, the limit means limit of sensing, limit of computing, right? So as it is, ultra sensitive. See what I've discussed, that quantum computing is successful. Yes or no? Just tell me. Today, 2025, is so much successful. Yes or no? First, give me the answer.
No, sir.
No. Why? Because of the noise. You will not get good efficiency because the environment and all the things and the hardware and software, they're not so much sophisticated to handle the high-end computing, right? Clear? And that is the reason, as it is very much sensitive, so we are using the quantum as a sensor. So as we are using the quantum as a sensor, so sensitivity is so much high, it can go beyond the limit, beyond the quantum limit. Quantum limit means the top level, means limitations, means upper limit, right? So it can go beyond it. If we can design a quantum sensor, I'll show you one of the biggest example of quantum sensor. Can anyone tell? We are using it for a long time. Can anyone tell what is a quantum sensor we are using? Everyone know the name. All the 102 participants, everyone know the name. The machine name is called MRI machine. You heard about MRI?
Yes.
Yes.
MRI machine uses quantum sensor, right? Which goes above the limit, means that there is some standard limit it can suppress because of quantum state entanglement. I'll show you what is entanglement. So there are various levels. So these are the properties, right? What is entanglement? Can anyone explain? What is entanglement? It is observed here, affected there. Something is observed here, it is affected there, and this distance can be 100 meter, it can be 100 kilometer, it can be 10,000 kilometer, it can be any distance. Observed here, affected there. So it can go any distance. So this is the very beautiful property of quantum entanglement. Let's see one example. So there is a story. Okay, Alice and Bob. I think J.K. Montes has also mentioned the story of Alice and Bob, right? So Alice and Bob lived in Australia or any country. Okay, they were grown in different cities. Say one in Sydney, one in Melbourne, right? And there's even two. Suppose they met in a college, they joined the same college, and they fall in love with each other. And subsequently, just listen the story steps. Event 3, they get married to each other after the college, and they're happily, married, and they got, that Alice got pregnant. And what happened? Unfortunately, after a few months, Bob has to shift to United States from his job for a job, but leaving Alice in, say, Melbourne, right? Even 5, even 6. After the days gone, after several months, Alice gave birth to a child. The last step, Alice gave birth to a child, and Bob became father, even without knowing it. So Bob becomes father, right? He changed the state of father. Although he is, not in Australia, he is in another state. So quantum entanglement is something where Bob and Alice, they got entangled when they got married. Here, Pushpendra sir.
Yes, sir. Yes, sir. Yes, sir.
So it is, see the first definition, when they got married, they entangled. If you have seen I can give another example. Lot of movies of, say, Salman Khan, there is a movie Judua. Have you seen it? Anyone else don't see the movie? There's a movie Judua that where Salman Khan, someone is beating him here in one place, he's getting affected in another place, right? His brother is getting affected in another place. So this is one example of quantum entanglement kind of thing, right? So this is an analogy with the quantum entanglement. So what I have started discussion, just remember this term. See, observed here, affected over there, and the distance can be any distance. It can be in moon, it can be in Pluto also, it can be anywhere. So distance does not matter. So this is the beautiful property of quantum entanglement. This property exists in case of quantum hardware, quantum dots, quantum systems, right? Something is called quantum measurement. What is that? After the one parameter of that in the laboratory, position or the energy can be measured. Either position or the energy can be measured. Quantum uncertainty principle, everyone know. After the measurement, the system is said to be collapsed into eigenstate to the operators. Okay. So this is called quantum measurement. I will go it slowly. So if we see, can you understand? If someone is measuring, the particle changes position. So we have duality property. This is the particle, this is the wave. So when someone is observing, this person started walking. So it becomes particle. So no one is there. This wave is jumping in joy, right? Again, it starts observing, the system collapse. This is called quantum measurement, right? Or quantum collapse, right? So there are a lot of bases of alpha, beta. I'm not going in detail. Already previous speakers mentioned that how this quantum state works. See, 0 and 1 can exist together. So it is called entanglement. See, it can be any distance. Alice and Bob can be any distance. They are all entangled together, right? Suppose you can see it is Saturn, right? This is Earth. So you can keep them any distance. So quantum communication is possible to any distance using this quantum entanglement, right? I think everyone know this picture, right? Saturn picture, this Earth. You can go to any distance for this kind of communication. It's possible in quantum. There is the beauty of quantum computation, entanglement, right? So, okay. So quantum surface is extremely sensitive. You know, quantum surfaces are extremely sensitive. It is made up with the quantum dots. See the state change. If you see the state change of the electrons based on the spins, electron spin. Just see the picture. It can change the state based on the electron spin. Quantum mirror correction, quantum surface design. Yes. So if you see the quantum, I want to go to the quantum system, how it works, and just wait. Now if you see what is quantum sensing, we're coming to this position. What is called quantum sensors are technology which is vastly used for high accuracy measurement, right? High accuracy measurement in the atomic level measurement. It can measure in the atomic level, right? So quantum interference, quantum coherence, quantum entanglement, already I've mentioned this. They're very interesting. It's called quantum magnetometers, quantum gravitometer, quantum gyroscope. So many other sensors are there. They're all different types of quantum sensors, and it can probe. Quantum states can often involve initializing the state, all quantum states, right? And it can determine the parameter of interest of high precision. So there is some structure called NV center. Anyone heard about NV center? NV center is nothing but nitrogen vacancy center in diamonds. It is a nitrogen vacancy centers in the diamonds. What is actually happening? This is the picture of a diamond, and diamond there is something is called nitrogen vacancy. Nitrogen, there is one vacancy. It's called NV center, nitrogen vacancy. These NV centers are very powerful. If you see, this is a carbon state, carbon and nitrogen. This is the carbon and nitrogen. This is called NV center. When the laser or many materials goes to this place, it can give the fluorescent light out of it. Hello, can you hear me?
Yes, sir.
I want to show you one video.
Yes, sir.
Light, temperature, pressure, heat, and more. But these sensors are self-calibrating and their measurements don't drift off over time.
Debashis, your video is not visible.
Yes, sir.
Audio
Your
is
video
coming.
is not visible, sir.
I've not started. I've not started. Just wait. I've not shared. So
Okay. Please go ahead.
Light, temperature, pressure, heat, and more. But quantum sensors harness the laws of quantum mechanics to measure things that are imperceptible to more traditional sensors. And because quantum sensors depend on constants of nature, their
can you see
reliability
it now?
never degrades. In other words,
Yes,
these
sir.
sensors are
Yes, sir.
self-calibrating.
Yes, sir.
Okay, just a minute. I'm starting from the beginning. See, it is very
And their
simple.
measurements don't drift off over time like traditional sensors do. Unlike some other pieces of quantum technology, quantum sensors have understand the world around us at an unprecedented level of detail. So, what's the real difference between a classical sensor and a quantum sensor? Both can measure different properties of the environment, light, temperature, pressure, heat, and more. But quantum sensors harness the laws of quantum mechanics to measure things that are imperceptible to more traditional sensors. And because quantum sensors depend on constants of nature, their reliability never degrades. In other words, these sensors are self-calibrating and their measurements don't drift off over time like traditional sensors do.
You know, sensor has battery, right? Every sensor is a battery. Yes or no? But in case of quantum sensor,
Yes, sir.
there is no degradation because they do not use any battery. So they are always on, means they do not degrade. You know, their performance remains today, tomorrow, and after 1,000 years also it remains same, right?
Both can measure different properties of the environment, light, temperature, pressure, heat, and more. But quantum sensors harness the laws of quantum mechanics to measure things that are imperceptible to more traditional sensors. And because quantum sensors depend on constants of nature, their reliability never degrades. In other words, these sensors are self-calibrating and their measurements don't drift off over time like traditional sensors do. Unlike some other pieces of quantum technology, quantum sensors have been around for decades. For example, MRI machines use quantum sensors and have been around since the 1970s. Inside one of these.
So you understand that quantum sensing, this is the technology, quantum computation exists since 1970. So this is not a new technology, right? Sensors are used since 1970, mind it. And it is used in our MRI machine. So if you see the MRI machine anywhere, any hospital or any diagnostic center, they all uses quantum sensing, right? Let's see how it happens.
MRI machines use quantum sensors and have been around since the 1970s. Inside one of these machines, the very atoms in your body are turned into individual quantum sensors. MRIs use magnetic fields to manipulate a quantum property called spin within your body's atoms. And the response of those spins to the magnetic fields can be measured and transformed into an image.
So, so what are the molecules? It means micromolecules or the quantum molecules within our brain? Using the that MRI machine, have you heard about 1.5 Tesla machines are available? So what they are doing actually, they are actually doing the orientation, changing the orientation of the molecules in the quantum state, right? Using this kind of NV centers and all these things, and that is changing our image, brain imaging. That is one of the part of brain imaging. So it can measure, transform the image. The atomic clock, one kind. This is actually the quantum sensors, right? They are manipulating using the magnetic field. They're changing the orientation of the molecules within our brain. Just see this video carefully.
Are turned into individual quantum sensors. MRIs use magnetic fields.
I'm repeating again, just listen carefully.
The very atoms in your body are turned into individual.
See, every atom of your body is turned into a quantum material. See, just listen carefully.
The 1970s. Inside one of these machines, the very atoms in your body are turned into individual quantum sensors. MRIs use magnetic fields to manipulate a quantum property called spin within your body's atoms. And the response of those spins to the magnetic fields can be measured and transformed into an image. Atomic clocks are another kind of quantum sensor and have been around since the 1950s. They keep time in GPS satellites and even define the official SI unit of a second. But things have changed since then. Modern innovations are making new quantum sensors and applications possible. One of these newer technologies makes use of nitrogen vacancy centers, or NV centers, which can be found or fabricated within diamonds.
See, modern all the quantum sensors are diamond, mind it. We are artificially creating an NV center, nitrogen vacancy and the carbon, within the diamond, and these diamonds are very powerful sensors, right? And this is used in every kind of quantum sensor. Shoma madam asked a question that these machines, quantum sensors, are costly. Answer is yes, costly, because they are made with diamond, and everyone knows the cost of diamond, right? So all the diamonds are used to, like a helmet. I'll show you a picture. We can wear a helmet. You have to give the magnetic field in the helmet, and this magnetic field in the helmet, using this diamond thing, it will show the image of your brain. The concept is already developed in India and various other places using this NV center, that you will wear a kind of helmet. Okay, this is a part of NQM, National Quantum Mission. Anyone is interested, they can work in this project. It's called NV Center project, right? Where the quantum sensors are playing a major role. It will show that how these NV centers are created within this diamond. See this picture very carefully.
Centers, or NV centers,
NV center,
which can
nitrogen
be
vacancy
or
center,
fabricated within diamonds. Pure diamond consists of a perfect lattice of carbon atoms. If two of those adjacent carbons are removed and one is...
Now using the laser, we are removing the two atoms, and there is nitrogen and this one is vacant. This one remains vacant. So NV, nitrogen and vacancy, that forms a pair called NV center, and this NV center is called, they can do the entanglement, and it's very powerful entanglement.
It's replaced with a nitrogen atom, then the nitrogen together with the hole or vacant spot function as an incredibly sensitive magnetometer.
Magnetometer.
That magnetometer uses electron spin to detect tiny changes in magnetic fields. In fact, NV centers are sensitive enough to detect changes that are 50 million times smaller than the strength of Earth's magnetic field. And even more impressive is that they can accurately detect those tiny changes despite the presence of the Earth's magnetic field in the background. But what does that really mean? Well, to put it in the context of a camera lens, that'd be like having a single lens that would let you stand in one place and zoom out wide enough to capture all of Mount Everest in a single image, and also zoom in close enough to clearly see a single human hair at the top of it.
So it is so powerful, even you can see the single hair of the person who is standing on the Himalaya. See, single human hair on the top of Himalaya, that can be, it's so sensitive. Quantum sensors are so sensitive, it can be measured, right?
Mountain. That kind of
Just see
sensitivity
this.
impressive is that they can accurately detect those tiny changes despite the presence of the Earth's magnetic field in the background. But what does that really mean? Well, to put it in the context of a camera lens, that'd be like having a single lens that would let you stand in one place and zoom out wide enough to capture all of Mount Everest in a single image, and also zoom in close enough to clearly see a single human hair at the top of the mountain. That kind of sensitivity can be used in medical devices to help diagnose disease earlier, and it can be used to navigate by sensing the Earth's magnetic field while flying in an airplane, driving a car or ship, and even while underwater and underground. And these same quantum sensors can be used to measure the tiniest magnetic fields within living cells, which can accelerate drug discovery. MCKVIE sensors are just one example of this new generation of quantum sensors. Others are in various stages of development and can be used to detect minute changes in properties like acceleration, rotation, pressure, electric fields, temperature, and even gravity. There are many applications of this next generation of quantum sensors, with creative engineers regularly developing new ways to use them. So, what does this mean for you? Whether you're an engineer interested in quantum, a product developer looking for a better sensor, a user of high technology, or a student looking for inspiration for what to study next, you'll want to be sure to keep an eye out on the future of quantum sensing.
Okay.
Teenagers are building businesses with AI, while the only AI you know is ChatGPT.
I think you got some idea, right? Some basic idea.
Yes, sir. Absolutely.
So see, diamond is the thing which is trading costly. Kumar madam, your question.
Sir, another thing, will it work in microwave frequency range?
Yes. Yes. Any sensing, any kind of range it can sense, right? And can you tell me that is it possible to reduce the cost? Anyone can say, or you can try.
Yes. Sir, again, please.
Can you reduce? Diamond is costly, yes or no?
Yes, diamond is costly.
So the NV center creation, and you see the NV center, right? Nitrogen vacancy center. So that is also again costly method, and system is totally costly. But can you reduce it? Can anyone say? Can you reduce the cost? How? Gaurav Gupta here mentioned yes, it is reduced. How? How it can be reduced? Can you just think, artificial diamond? What is artificial diamond? The artificial diamonds can be prepared, and in similar kind of carbon NV centers, we can prepare for, in a reduced cost. Maybe possible, right? Maybe you can think in this way. So this is actually the structure where the pole of electromagnet and diamond is placed, and this is actually measurement steps, right?
Sir, we can go for the chemical vapor dissipation, right, sir?
Yeah, various other techniques are there, yes. Quantum sensors, they uses the quantum entanglement I already mentioned, and accelerometer, gravitometer, so many other things, right? So NV centers are playing a major role for even various kinds of photolithography measurement and all these things. They can control the spin. Control of spin can be done using this NV centers, right? So so you see there are so many applications, clinical applications. Like you can see this OPM probe array. You can probe multiple NV centers on your brain. Okay, and that can measure take the image of the brain, right? Some companies, leading companies in Calcutta, along with IIT Powai, and they are working in this project called MRI helmet. You'll wear a helmet for a few minutes. There will be a magnetic field using NV centers, and you can measure the MRI image of your brain. This is possible. Okay. Also, NV centers can be used for cellular, the probing. Dense NV center ensemble can measure the electrical activity studies and cellular, all these things, right? Various other metabolic studies can be done, right, using these NV centers. So many applications are there. Even it is so sensitive. I think if you heard the video, then we said that if there is a possibility of volcano means something is happening inside. Your NV centers are so sensitive, they can understand. It can generate the alarm. Quantum sensors can generate the alarm for volcanic activities. So there are a lot of companies, a lot of Glasgow University, they have developed a NV center kind of structure in a small chip. They're placed in the volcano. The Italian volcano, they put with this kind of sensors near the volcano, which can measure the possibility that, okay, within 7 days volcano will erupt, and please vacate the place. That can save the life of thousands of people, right? So there are a lot of sensors, not only in healthcare, also for prediction and various other sensing mechanisms. So quantum sensors are so popular. And see, this is an intelligent device, yes or no? And this is providing intelligence at the edge. Can we not call it as a quantum edge intelligent device? Can you call it as a quantum edge intelligent device? Yes or no?
Yes,
Sir,
we understand why you have given the name.
Sir, are you showing any slide?
Yes.
Slides are not visible actually.
Not visible. I'm showing it for a long time. One second. Okay. I'm showing it to you.
Yes, now it is visible.
I don't know from where you have not seen. Okay, see this one. This is a volcano picture you can see. Volcano picture you can see.
Yes, sir.
Yes, yes, sir.
This volcano, we have 40 tiny galvanometers made up with this kind of NV centers, and they put this NV center within this small chip, and this chip is placed in various places of near the volcano. It can predict, it has an intelligence, sensing intelligence, sensor with intelligence, right, which can measure when the volcano will erupt. Then this is acting as an alarm system to the nearby people in that Italian cities or any places where this volcanic eruption occurs. So this is the edge device, right? This is also giving alert. So can you not call it as a quantum edge intelligent device? Can you call it as a quantum intelligent device? Isn't it? Using NV centers? Yes or no?
Yes, sir. Yes, sir.
So this is just one example. Now people are using machine learning and other techniques to combine this, extract the more information properly, various either deep learning or LLM based techniques to get the data. So this is all the device called quantum edge. I've started my discussion what is edge device. So this is the NV center based quantum edge intelligent device, right? Even this quantum edge device can, this NV centers are used, believe it or not, during the COVID time to measure the virus, right? COVID virus, to understand the nature of the COVID virus, right? So quantum sensing is an atomic scale it can sense, right? Atomic scale. So using this quantum engineering, we can perform these various jobs, right? Can you see this picture? This is the most important picture. It can do the brain scan, and we have the NV centers, using brain. Have you gone? Have you seen this MRI machine? So big, right? You have to go inside the machine. Anyone has seen it? You have to go inside the machine and through automated chamber, and your body will be scanned with the NV centers, right? Now see, this is a portable version of MRI machine. You are wearing this helmet, and just for information, this helmet is prepared in India, and it is possible to measure this mechanisms, means brain images, just by putting the magnetic field for a few seconds, right? And this is a edge device, edge intelligent device, beautiful device, right? Magnetic device or magnetic helmet which can measure your brain image. Brain imaging is possible. Any abnormalities, anything, brain imaging is possible using this device. So this is the edge device. This is a consumer device. Agree? Consumer electronics. So quantum based consumer electronics possible to give the service at the edge. And just you'll be happy to know this is happening in India, and this is not from outside India. So you must be proud, and we can contribute. Means we can contribute, and very interesting. This similar kind of edge devices are possible to prepare. And you'll be happy that the Calcutta also doing research in sector 5, also in that some of the Newtown area, they're preparing this brain imaging kind of sensor, right? So this is also one kind of edge device, right? So I hope that within a few years, I think it will be commercially available. It will be commercially available to everyone. Those who can use this this helmet, this this consumer electronics helmet as a sensor using NV sensors, right? Quantum sensors. So these are the beautiful application of edge intelligence. Yeah. And if you see which IIT, and if you see around, I think 8,000, 9,000 crore they have given for this commercialization for this NV centers and based sensors, right? I can tell you the TCS Innovation in Calcutta, they are working with IIT Powai. They have a center, means a brain imaging center. There, if you go to their website, this all quantum sensing lab. There is a quantum sensing lab. Only one lab. I hope that in future similar kind of labs will be coming up in various part of the world, and we'll be using these quantum sensors. This is an intelligent sensing. After getting the data from the brain, then we can do the machine learning techniques. Everyone know this deep learning or generative AI, so many things. So this is a very interesting area how this edge things works together. There's some interesting technology called SPIDS, superconducting quantum inference device. Okay. Currently, MEG scans performs with sensors called SPIDS. SPIDS are very popular, but they work in very low temperature. But people are working in using these NV centers for normal temperature as well, right? So we can measure the Alzheimer patient. That anything possibility of Alzheimer or anything problem in the system, millimeter level. That wearable quantum sensors can measure this brain activity, right? One wearable quantum device that can measure this kind of activities. Okay, so this is actually revolutionizing the quantum computing world, and you'll be happy to know that India is leading in this area of quantum sensing. Always we are blaming, but we should appreciate that the government of India is spending generous money. Even anyone listening to this talk, even those who are interested, I can connect those people. I have their contact details. This is a very interesting area is going on. A lot of things can be done using these quantum edge devices. Right? See, quantum sensing is used by oil and gas industry. I can tell you Reliance, TCS. See, this is a website of TCS. I just copied from the TCS website. Quantum sensing is used for oil and gas detection by the industry. So using these edge devices, using this edge cloud platform, this quantum sensing is possible. So we are calling it quantum edge intelligence, right? Whether that is helmet or any kind of things, This quantum sensing is extensively used for oil and gas industry. It is practically used not only today, it is used for several, maybe 1 decade, right? They're using it. So if you are interested, they can go to this TCS website, they can go in detail how it works, right? So quantum sensing, we have heard, we have gone through this, what is quantum sensing already. Now AI comes into picture. We call it quantum AI, QAI, where we actually talking about high precision sensitive and precision measurement. We heard about precision agriculture, right? Anyone know what is precision agriculture? Shubha madam, are you there, or Pushpin sir?
I'm
No,
there,
sir.
but I don't know, sir.
I
You
haven't
heard
heard
about
it,
precision
sir.
agriculture. What is that? Precision agriculture?
Now the sensor is used, or IoT device is used, that is related with the precision agriculture.
Exactly, madam. Exactly, Shubha madam. That
But
precision agriculture is used actually to precisely to find out which leaf has affected, right? Using the IoT. Clear? So using the sensors. Similarly, we are using precision measurement, precision healthcare, using high sensitive, ultra sensitive, quantum and edge intelligent devices. Clear? So they combines quantum sensing and AI driven inference. See, already you have seen quantum sensing, right? Now we have to come to the inference, AI driven inference, which can help to solve the complex industrial problems, means consumer electronics problems, leading to significant economic benefits. It is also coming to the that we want to make it in the lower cost as well, right? COVID based see, quantum sensing already I mentioned, using microfluidic device. They also use quantum devices, probing the cells and molecules, molecular level. Even quantum sensor is used for drug discovery, healthcare, and various other applications. Many companies, University of Chicago, the physicist Peter Muller, they are using this quantum nano diamond sensors for as a thermometer, quantum thermometer. Can you imagine? We heard about thermometer. Now we are talking about quantum thermometer. Exactly, precisely, up to 4-digit level, we can tell what is the temperature, right? Exactly, we can measure using this quantum thermometers. Okay. Most important, gene expression analysis using quantum sensors. Very important. Gene expression. You know that everything is written in the gene, right? If I can read your gene, I can read yourself. Yes or no? Everything is written there in the gene, that how you will perform, how you will behave, what will be your disease or everything, right? So gene contains every information. Now gene expression can be also measured using quantum sensors. What is that? You can imagine the CEO of QNext, there's a company called QNext, he has mentioned that you can imagine using some atomic scale thermometers to investigate the temperature, influence the cell division, gene expression, and how the molecules go in and out of the cells, and all the major questions in medicine and biology. So everything can be measured. If you can see the atomic scale thermometer, we can measure the gene expression as well, how the molecular interaction happens and everything, right? So these are all the new technologies coming up. Quantum thermometers can give you the exact gene expression and gene analysis and all these things. These are the various new aspects of quantum computing, which is actually, this is the edge device, quantum thermometer. This is the edge intelligent device, which provides ultra scale, ultra fast operations to perform this molecular level computations, right? See, already I mentioned quantum MRI. I'm not going in detail. Quantum sensors that can perform the MRI in single molecule to understand the relationship between their structure and the function, which could radically improve the performance of understanding for medicine. So we can give precision medicine, individual medicine. That means if you use this helmet For Debashis, it will give different result. For Shoma madam, it will give different result. From Pallav, will give different result. So we can give different personalized medicine if we can understand the quantum MRI image for each and every individual. So it's called personalized or precision sensing can be done using this kind of imaging and processing techniques. Right? So quantum MRI is playing major role. Programmable device, quantum sensors, we can program it using various other scaling it devices. So future sensing is actually atomic level sensing and portable sensing. Okay, portable means I've shown you MRI big computer, big screen becomes a small helmet, right? So that every consumer can use it in a very in a doctor's chamber. Immediately, doctor can understand what is the problem, right? So quantum IoT, quantum applications, which is coming in a big way for various application in various places, right? So I'm not going in detail, but what I can tell you that quantum aggregation from various learning, from local level learning to global level aggregation, that means quantum federated learning can be performed using these edge level devices. We call it quantum aggregation, quantum federated learning. So these all things are possible, using quantum sensing. Now quantum enables devices which can provide 6G, 5G, all these things, lot of applications. You see, lot of applications are there for quantum sensors. And if you see this quantum sensors, quantum surveillance, if you put the quantum sensors at the border, it can, one quantum sensor can replace thousands of military. And India is also, every country is working on this quantum surveillance. Can you believe it? One quantum sensors in the border of we are friendly, isn't it? We have very friendly neighbors, right? They love us so much. We need to give the surveillance in the borders, right? So we can deploy these quantum sensors to find out whether anyone is crossing the border or not. Whether it can be India-Bangladesh border, India-China border, India-Pakistan border, or any border. Whether it's coming through the underwater, through say Chennai, that is also, or Visakhapatnam, that can be also done. So quantum surveillance is the new generation of quantum edge intelligence, which can provide the services at the edge, right? See, we can provide real-time distributed computing. There's a company called Quantum Edge IQ Ready, which provides quantum edge intelligence information processing at the distributed system. AQRI Ready. These are the various companies are coming up. That means it's been getting commercialized. Quantum computing is getting commercialized as well, right? So I think I have to stop here. It's almost 9:30. I think I've given some idea how this quantum sensing works and how this quantum AI and quantum deep learning, quantum generative AI, they are all coming together to help this sensing to make the world environment intelligent quantum edge or quantum edge intelligence to provide the services for the human being for a sustainable society. Okay, thank you very much.
Thank you very much, sir. What else we can say? Such an informative session, even if some of the informations that was not known to us, right? Like the MRI, which we knew about MRI, but some of us we didn't know about. It utilizes this quantum sensors. Really, sir, such an informative session. Sir has covered from quantum age, quantum dots, up to classical and quantum computing differences, and up to the quantum sensing, etc. Sir, what else I can say? Such an informative and what a great deliberation. So it is my request to the participants, if you have any queries, kindly raise your queries through the chat box, or even you can unmute yourself and directly interact to Professor Debashis. Any queries?
And just Pushpendra sir, that within 2-3 years, if it is required, we will be all using this helmet, especially the helmet, and it
Yes,
is
sir.
in the process of commercialization. in India.
Okay, sir.
So
But
hopefully we'll get it. We'll
that
be using it in future, near future. Within
okay,
2-3 years
got it.
maximum.
Yes, yes. So request to the participants, if you have any queries, kindly post your queries. Actually, sir, during the sessions, the
Yeah, there are a
participants
lot
has
of
already
yes.
already interacted,
Yes.
and whatever they have posted to the chat box, it is just an appreciation to you, sir. So, um,
Thank you everyone for
so
staying. It's almost 9:30. Everyone, I can see around 90, 97, 100 plus
Sir, is
participants are
there
there.
any
Thank
scope
you.
to work with the quantum? Actually, we know that only in Kolkata,
Yes.
that is our idea, but we don't know. In TCG Crest, there is a lab in quantum lab.
See, there are a lot of quantum labs
Because
in
the
Calcutta.
temperature we need to.
Yes, yes, carry on.
Yes, the temperature which we need for quantum lab setup, that is very low temperature. So what we do
No, madam,
normally,
that
the
is not
people do
required.
the
That is
simulation.
not at all required because NB centers can be done in room temperature.
Yes.
So that does not require any low temperature problem. And that is the reason quantum sensors are there for 1970, mind it.
Okay.
So no low temperature. It is room temperature possible. And you'll be happy that many of my students, they are also working in this quantum sensing devices within India and outside India. So anyone is interested, there's a lot of scope is there, huge scope is there. But you have to give time.
sir,
Yeah.
yes, sir, there is a query raised by one of the participants, Kaushik Mukherjee. He has raised, what are the major differences between classical sensor and quantum sensor?
See, already I have given in the one slide that
yes,
it is ultra sensitive. Classical sensor, they physically they change. That temperature sensor means there is a transducer which can convert the temperature to electrical signal, right? So there is a transducer physically, but in case of quantum, it is changing the state in quantum entanglement state, right? There is no physical temperature. Quantum and classical sensor uses battery as a charging device. In quantum sensor, there is no battery is required. It is just changing the state. There is no degradation in the performance. In classical sensor, if you put the sensor anywhere, it will degrade after say one month. But quantum sensors, it can work years and years and years with very high sensitivity. It is at least several thousand times faster, real time, and ultra sensitive. So quantum sensor, there is no comparison. It is ultra fast, right? So this is the I've shared the slides also. There are a lot of advantages are there. Quantum sensors are so popular. That is the reason.
Hopefully, Kaushik Mukherjee, you have got the
replied,
response from Professor De. Sir, one interesting thing, one of the participants asked about your email ID. Most probably wants to contact in future. Is it possible to share in the chat box, or you, once our FDP is over, the way that we can share your email ID?
I can share it, no problem.
Okay, sir. That's great.
So, yes, I've shared it. Okay.
Yes, participants who has raised the queries, sir has shared the mail IDs, and even the contact numbers too.
Yeah,
Thank you,
WhatsApp
sir.
number. Do
Sir,
not call, just you
yes,
can send
sir,
WhatsApp.
Yeah. Sir, another query. Sir, Mr. Shayonde has raised another query. Sir, the LLM or QLM part, we want more from you. That means he wants more regarding LLM and QLM part. Is it possible to cover it right now?
It is a vast topic. This morning I was see. Can you see my slide? I cannot cover because it takes, this morning I was giving a lecture on QLLM or quantum large language model.
So is there any future program of yours so that Mr. They can attend this session?
Quantum large language model, they are using transformer. This is the model of transformer, right? I have given a four hours lecture this morning, right, on this topic, quantum LLM. In case of transformer, there is basically ChatGPT is nothing but transformer model, right? Everyone knows ChatGPT. Input embedding, positional encoding, encoders, decoders, multi-head attention model, which is used for contextualization, normalization, and output layer. This encoding and decoding, they are using quantum encoding and quantum decoding, right? And that becomes ultra fast and ultra sensitive. So that is the reason we call it quantum LLM. That is the difference between normal LLM to quantum LLM, and that becomes ultra fast. So we are calling from generative AI to quantum generative AI. So see, so many things are there. I cannot cover, it will take another 2-3 hours time, right? So I just want to show you some of the slides, how it works, and the LLM to quantum LLM, right? Just see the slides. I am not explaining it. So there are some challenges of generative AI. It takes a lot of time. The time can be reduced in case of quantum LLM. So
And we have another query, sir.
yes, just a minute. You know that.
Yeah.
See, quantum computing and generative AI, they're combining together, right? Generative AI provides high-speed computing, right? Means generate the events, right, through the tokens using the transformer model, and it takes a lot of time, lot of power. If you use this quantum computer and generative AI together, that is ultra fast. Here, so what is the limitation of generative AI? That can be removed by quantum computer. That's why we call it Gen QAI, generative quantum AI, right? So quantum data to AI using this supercomputer. It's a new era of called quantum AI frontiers called Gen QAI. This is a very interesting area, and a lot of people are working. And I told you that quantum encoder and quantum decoder, they are used. See, they are the quantum circuits now using Amazon bracket, or see there's a generator, discriminator using the quantum gates, right? So it becomes ultra fast. Generator, discriminator, which is possible in case of quantum sensing. See, these are the all biological molecules and also medical fields. They are using this quantum, already using this quantum generative AI. Okay, thank you. Yes, another question you asked.
Sir, last question. Prakash Kumar Jha has raised another question. Could quantum sensors be applied in detecting gravitational waves or dark matter?
Yes, quantum waves can be used for gravitational waves. Especially, I have given that gravitational sensors for like a volcano and volcanic eruption and everything that can be used. Yes, and I've given 4 or 5 types of quantum sensors: gravitational, magnetometer, so and so, right? So everywhere there is application, various applications using NV centers. Yes.
So hopefully all queries have been answered. Sir, we are very fortunate enough to have you with us for this second session. So definitely participants, once our FDP is over, from our end, we'll definitely share the slides that will be shared by our respected speakers. So no more queries yet, sir. Thank you once again.
Thank you. Thank you very much.
Thank you very much. Good night, sir. So good night, participants. Tomorrow we have our day 2, and we will start our tomorrow's session sharp at 6 p.m.
Thank you.